To Physics 2 on this cold snow day. Hopefully you're in a warm place and didn't have to go out in the ice. All right, so I had a request to look at, I think it's the last one of our homework problems in Achieve, and get some hints here. So let's just look at this example here real quick before we move on to today's topics. And so I think it gives you different setups, each person a different setup, but we have two charges and we have a test charge or just a point that we're trying to determine the electric field at the origin. And so your points might be in different positions, hopefully are with different coordinates, so I'm not giving you the whole answer here, but I had some requests here. And so part of this problem, I think maybe the trickiest part is just getting everything encoded into Achieve the correct way. But let's go, because this problem is very much like what we did in class on Friday. But let's just do some setup and talk about it a little bit here and see what we can do. So, and in this case, we've got two charges that are the same size, value q for the charge, little q, and then the test charge is having a positive, or is capital Q, and we generally assume test charges are positive, and I think this one is as well. And so we're going to calculate actually we want the force on a test charge in this position, so let's just call this one 1 and this one 2. Get my colors working here. This one 2. And so thinking about the force from charge 1, right? Remember, we always have the force acts on a line between the two, straight line connecting the two, and let's just figure out the magnitude and direction, but let's do a sketch first so we can get the right direction. So two positive charges, they're going to repel each other. So the charge at this position is going to be pushed away from the charge up there. So we're going to have something like this for F1, right? For F2, it's a negative charge, negative Q, and so positive charge will be attracted to it. So it's going to be pulling towards it. So we would have a force in this direction. They have the same size, so magnitude-wise, in terms of charge, all the charges are the same size, so the forces would be the same length, but this one is closer, right, by the hypotenuse compared to the side of a triangle. And so let's make it a little bit longer, something like that. So this would be F2 as F1 as a vector. And so adding them together, remember, if you want to just do it pictorially, make a parallelogram and you add them together, and then the diagonal is the total, something like that. So we're expecting in this case to have a positive I component on the total force and a negative J component on the total force, just as a check. All right, so let's do F2 first, and so F total will be, of course, F1 plus F2. Right? They don't give us any, I think they give us the coordinate values, but they don't give us a value of Q, and so any of the Q's, so we've got to do it algebraically in terms of these Q's. So let's do the easy one first. So F2 in terms of direction, let's just get that done. So the direction of F2 is just in the x-axis direction, so it's just going to have an I hat for a direction vector, and of course it's going to be in newtons eventually, but for this one it doesn't really matter, we're doing it symbolically. All right, so remember a force equation, Coulomb's law, K Q1 Q2 over R squared R hat, right? And in this case they say they don't want it in terms of K, they want it in terms of epsilon naught. So K is 1 over 4 pi epsilon naught, so we're going to have to put that in there eventually, but let's work on the other parts first. All right, so in this case we want K, and then the two Q's, little q and big Q. Oops, little q and big Q are the two different charges that we're talking about here. R hat is the I hat. Anyway, left too much space there. And then what goes on the bottom here is the distance between the two squared. In this case, this one is at 0, 0, and the little charge 2 is over here at 3, 0, so the distance is 3. So I don't know if they gave us any units on this problem. Anyway, we'll just put in 3. I think that worked, as I recall when I did the problem. All right, and so in this case then, I guess we better put in let's put in 1 over 4 pi epsilon naught for k. And so we end up symbolically with little q, big Q, I hat. In achieve, it's just a bold I. The books often do that. And then we'll have 4 times 9, so 36 on the bottom, pi epsilon naught. Something like that. That would be F2. All right, F1. Do it similarly. Magnitude-wise, going to be Q over 4 pi epsilon naught, and then the distance squared. This one, the hypotenuse here for my problem, this side is 3, this side is 2, so this is the square root of 3 squared plus 2 squared, so that's the square root of 9 plus 4. Square root of 13 is the length is r, but then when we square it, the square root of 13 squared, so that's just going to be a 13 in the bottom there. And then we have to get the direction vector, right? And so the direction vector, again, you could figure out the angle and do it that way, or we can do it with the ratio of triangles. Let's just do similar triangles idea. So the x part is 3, and the magnitude is square root of 13, and that's I hat. Is it positive or negative? We're talking F1 here, so it's a negative on the I part, and it's also a negative on the J part. The J part is 2 up, or is, anyway, 2 is the side of the triangle, square root of 13 is a hypotenuse, and that's J hat. They're both negative here, all right? And so to get the total, I think I'm not gonna go through all of it, but to get the total, you're gonna add i's to i's, or this I and this one's a negative minus, and this one is gonna be, there's no J part, so it'll just be the J part here. So for example, the J part here would be negative 2q, little q, big Q, over square root of 13 times 4 pi epsilon naught, J hat, something like that. And then these two i's you'd have to put together, I components, and get some sort of a fraction, a number fraction, and then still it's going to have k, q, q, I hat, and then a pi epsilon naught also on the bottom. All right, so your numbers will be different, but you can go through, hopefully you know how to add these things up. Maybe you're lucky your calculator will do it in nice round number fraction terms for you, so you can get a nice equation. Enter that into Achieve. And so do be sure Achieve has places where you can enter in your unit vectors. Of course, it has pi. Epsilon naught is a little tricky, but there is an epsilon, and then if you do an underline symbol and then a 0, then it will make it an epsilon naught, so you can enter that into Achieve as well. So hopefully that gives you a good start, or gets you through that problem. Okay, so today's topic, we want to talk a little bit about our electric fields. So we started talking last time about electric fields. We talked about that they come out of positives, the field lines go out of positives and into negatives, that the vectors, the field is stronger close to a charge. We wrote the equation for a point charge. E is K, I don't remember what kind of Q over R squared, and then we have our R hat. So remember that the electric field is force per unit charge, or we could say force is charge times electric field. Either way, same equation. That should be on your equation sheet. And so, and then we talked about superposition, saying if we had a bunch of charges like we had on that previous problem, 2 charges, but if we had many charges, however many, we can just add up the effects, calculate the effects one by one, E component, E field, from each combination individually, and then add them all up and we get the answer. So if we have, what if we have something like this? Now we're going to have a whole line of charge. This is supposed to be like a half circle, or part of a circle, and I wanted it to be centered on my thing here, so that this is the same, it's symmetric about the axis, and we have some angle theta that we are using as our variable of integration we'll get to here, and it goes up to alpha and down to alpha. And so we want to know the field. What is the electric field at the origin again? All right, from this line of charge. All right, so we're going to have some little piece in here. We'll call it a dq of charge. All right, so we can get our integral stuff set up. And we need to talk a little bit about charge densities. So charge densities is just density of charge. How many charges per either length or area or volume. So we have lambda is the charge per unit length. Let's just say Q over L. And then that's the charge density for linear charge density we call it. We have what we have sigma, which is the charge per area. Okay, so a surface area kind of charge density. And then we have rho, which is the charge per volume. All right, so this one would be in coulombs per meter. This one is coulombs per square meter, and this one is coulombs per cubic meter. All right, and so various types of setups, we may use different types of densities. So that's just a little side note. I think that's on your equation sheet as well. So in this case, we're doing a line of charge. It's a curved line, but still it's a line of charge, so we'll use the lambda kind of idea. And so our little bit of charge here is going to be our dq, like I said, and it's going to be lambda times ds, if we're taking s as the length of the arc length here. And so, and then ds, remember going back to trig or even stuff we talked about last semester, is r d theta. All right, and so dq oops, I lost my lambda in there. All right, and so dq then is, so ds is r d theta. The lambda is multiplying the outside, so altogether then dq is lambda r d theta. All right, so we can take our angle, we can go from negative alpha to positive alpha as we integrate, and we can get the whole thing. So remember, integration is just the limit of a summation. Summation is just adding things up, and so integration means adding up every tiny little infinitesimal little point along this line, right, to get the integration. And so we're going to have a whole bunch of dE's then, little bitty components of the field from every infinitesimal little point. We're going to add them all up as we go around to get the total field, the total effective field at this point. All right, so our dE then, remember we're going to kind of start with this. So E is kq over r squared. So dE is k dq over r squared, r hat, and we'll just kind of leave those parts general for now. But then it gets a little more tricky. So let's say we're taking this point and we're calculating the dE from that. So where would that be? So remember we're thinking of a positive test charge, and let's just assume we're positive on this positive charge density on our line, and so the field will be pointing away. So this would be our dE field vector from this little dq part of the line. All right, hopefully that looks pretty good. And so that is at an angle theta from the horizontal, the x-axis, as you would. But we're in 2D, right? We've got curving things happening, so we're going to have to not just do a dE, we need a dEx, and we'll need a dEy. Well, let's work on x first, and then when we want to get the whole, so eventually when we want the whole thing, we're going to have to integrate, over our line. And so what would be the x component of this field here? Let's see. Let's make a bigger picture here. So let's pretend this is our dE expanded view from in here, All right, so we got our horizontal, and we got theta in here, and so we've got our DEX component, and then we're going to have our DEY component. All right, and so we're trying to figure out this one, again, expanded from in here, seeing that view. All right, so our DEX is related to theta, right? It's going to be, what is it, cosine theta or sine theta? Say it out loud. Cosine theta. All right, so DE in the x component is going to be DE itself, magnitude-wise now we're talking, times cosine theta. All right, and maybe I forgot something. It's in the negative x direction, so we get a negative on it to get the stuff right. So in terms of the triangle, it's cosine. In terms of the picture, we see it's in the negative x direction, so that's how we get our negative. And so let's plug in parts. So we've got our DE. Again, we're going to take the magnitude of it so we can forget our r hat and stuff. We're taking care of that with the x and y components. So we're going to have k. DE is, let's get my negative sign on there just so we don't lose it. Negative k dq. I guess we'll just write it in general first. dq over r squared, cosine theta. And then we need negative k, and then dq is lambda r d theta. Yes. And then we're going to divide by r squared, and we're also multiplying by cosine theta. Get all of our pieces in there. Looks good. All right, so now if we want EX, all of EX, all of EX, so we're going to take the x component for the whole E vector. All right, so if we had the whole E vector somehow in here, which way is it going to go? I guess if we're symmetric about here, we would expect the whole EX, actually the whole thing, to go this way. So just looking at the symmetry, if it were drawn better, half of the y's are above pointing down, and half of the y's are below pointing up. All right, and so the y's look like they'll cancel out. So the total answer looks like it's going to be the x, right? It's just going to all the x's are pointing to the left in the negative x direction, and so I think EX is going to be, just looking at it, you would think EX is going to be the whole answer, but we'll go ahead and check. So EX is going to be the integral of DEX, and we're going to go from negative alpha, well, DE. When we get it into thetas, we're going to go from, into d thetas, we're going to go from negative theta to negative alpha to positive alpha. So let's just go ahead and fix that up. And so we're going to go the integral of E dx, and so we're going to go, like I said, we've got it in alphas, or in thetas here, so we're going to take our limits as negative alpha to positive alpha, and let's just write it all, I guess, negative k lambda r cosine theta over r squared, and just write the d theta out here like we're used to seeing. Okay, and so looking at this integral then, the things that are constants in terms of, with respect to our limit of integration, or our integration variable, I guess I haven't really named r, but r would be, of course, the radius of this thing. So all of these points are r, right, including the one our dq that we're using as our test, or as our starting point. Right, so it's because it's an arc of a circle. All right, so r is a constant, so that can be pulled out, thankfully. K is also obviously a constant, and the density is a constant, and so we've got negative k lambda r, well, we can cancel out some of our r's. Negative k lambda over r, integral from negative alpha to alpha of cosine theta d theta. Not too bad. And so what's the integral of cosine? Sine, I think I heard. And so negative k lambda over r sine theta goes from negative alpha to alpha, and so we're going to have, negative k lambda over r, final minus initial, so sine alpha minus sine minus alpha, and minus sine of minus alpha is negative sine alpha, because sine is an odd function, so this whole thing becomes just another plus sine alpha, and so we get EX, hopefully this isn't going off the screen, negative K lambda R 2 sine alpha. I don't want to do that. Okay, hopefully you can still see that. All right, so our X component then of our electric field is here. Check my notes, looks good. All right, so like I said, by symmetry, we would expect that to be the whole electric field, but let's go ahead and calculate the Y component. Let me see. Well, maybe we can do it without looking at the picture. Hopefully you have it in your notes. So let's find EY. Well, let's find DEY first. And again, here's a picture. So DEY, again, is looking at the triangle. It's the opposite side of the triangle, so it's going to be DE sine theta. And it's also going to have a negative sign because it's going down, just to get our vectors right. Okay, so DEY is negative DE sine theta, and DE is, so we got a negative, and then we got K dq over r squared, and we're again taking magnitude, so we can forget the r hat for the time being, since we've got the x and y components. We're taking care of direction with x and y components, and so we've got K dq over r squared sine theta, and then again dq was, where did dq go? Lambda r d theta. Alright, so we've got our DEY, and then we want our actual full EY. To get that, we have to do our nice integral. Alright, and then we're going to again go from negative alpha to alpha of, let's just kind of rewrite it, negative K lambda r sine theta over r squared d theta. Hopefully I didn't lose anything there. Looks good. And then again, same argument, or we can cancel out some of our r's. Same argument. Theta is the variable. R does not depend on theta. Lambda doesn't depend on theta. K doesn't depend on theta. So pull those out. Negative K lambda over R, canceling out one of the r's in the numerator and denominator. And so what's the integral of sine? Negative cosine. So let's put this a plus. We're going to have cosine theta evaluated from negative alpha to alpha. All right. And so I kind of skipped a step. I didn't write integral of sine theta d theta. All right, just factoring. Hopefully you can see that. And then when we evaluate the integral, we're going to have K lambda over R, and then we're going to have cosine alpha minus cosine minus alpha. Right, but cosine is an even function, so cosine alpha and cosine minus alpha are the same thing, so these cancel out, equals 0. Woohoo! Yeah. Okay, so EY is 0. So just like we saw, hopefully we saw by looking at the symmetry of things, we thought it would be 0, it is. So if we want to write our whole E then, go back to our EX, it's right there, so E is just equal to EX with an I hat. So E is just negative K, negative 2K lambda sine alpha over R with an I hat. And not that units matter so much at the moment, but they're Newton per Coulomb if you got everything in standard units. Okay. If we, for example, want to take alpha to be pi over 2, or pi over 4, pi over 2. Yeah, take alpha to be pi over 2, 90 degrees, that'd be half a circle. And then, so what's sine of 90 degrees, or sine of pi over 2 is 1. And so we could get, for example, if alpha equals pi over 2, then, so we have a half circle, then the electric field from the half circle is negative K. Sine of alpha becomes sine of pi over 2, which is 1. So it's just be negative 2k lambda over r I hat. For example. Right, but for whatever alpha we have a general formula here that we could plug it in. Okay. All right, that was good. Let's try probably a new piece of paper and look at another kind of distribution. What if we have a whole circle? That's a circle, really. And some radius r, we'll use capital R this time. And we want to know the electric field going up on this axis. So what is E on the Z axis? All right, so we're going to have some point up here. This is our Z axis. So some value of Z on this point. And we're going to look at it in terms of, it's again another line, right? So we're going to have a linear charge density, but it's going to go around, we're going to go around this circle, the whole circle this time. All right? And so we'll have some little dq here again, which is going to be lambda ds again. And this time I think we'll just integrate on ds, so we'll leave it in terms of the charge part, we'll leave it that way. We'll need the theta in terms of the theta will help us to relate z and r, and we'll call this little r, I guess, to each other. All right, so just looking at symmetry, and we won't actually calculate all the parts, but thinking about this thing rotating around in the x and y direction, so I guess we can just kind of draw in xy coordinate system here. I don't know how we get it in here. X and y, in terms of x and y, which are, if we think of this as a ring sitting on here going straight up, x and y is in the plane of the paper, and think of this rotating around. Hopefully you see that as it goes around, there's a positive x, or a positive y, and negative y that are the same size. Same thing for x, positive x, negative x. So those sideways components are going to cancel out, just like we saw from the previous one. And so the only part of E, so E total, is just going to be EZ. EZ times K hat, for example. Okay? And so because the y, so EY and EX equals 0 by symmetry. Sorry for my writing. Okay? And so the only E that we're going to worry about, the only part of E we're going to worry about, which is be the total E, is the Z part. So we're going to basically say DE is equal to DE sub Z. And let's figure out what DE sub Z is. Okay? And so what can we do with this stuff here? We've got, this is R, this side is Z. We can say then that tangent of theta, just to get some relationships here. What's tangent of theta? Theta is here. Theta, tangent is opposite over adjacent. All right, so tangent theta is R over Z. Right? Or if we need cosine theta, what would cosine theta be? Adjacent over hypotenuse, Z over R. And just in case we need it, which we probably will, R is the hypotenuse of the triangle using Pythagorean theorem, Z squared plus R, capital R squared. All right, so we've got our pieces there in case we need it. We've got dq is lambda ds. We've got, remembering E, we just write it somewhere, just in general. E is kq over r squared, r hat. All right, so using all those pieces, we should be able to figure this out. So again, we're going to do magnitude-wise because we're going to take, kind of figured out the components using sine, cosine, tangent, what have you. And so dE, let's get started here. So dE then is going to be k dq over r squared. Let's look at my r squared there. And so, and then we said dq is lambda ds, okay, lambda ds. We're going up, so we got a positive. Things are nice here. And then r squared, and we can leave it for now, I guess. And and then we want to find the z part of E. So in general, dE is going this way, right? From this chart, this piece of charge on the line against linear lines. We got linear charge density times the length of the little infinitesimally small piece. And so dE is this way, but we want dEz, which is this part of it. Okay? So whole E this way, Z is the up part. This part can have X and Y parts, but we're going to ignore the, or we're saying they're going to go, we know they're going to go to 0 by symmetry. All right, so we got then theta is in here in between dE and dZ. And so if we want to do dEz, it's going to be dE, and then again, is it sine or cosine? Cosine. Good job. All right, so dE cosine theta. And so that becomes k lambda ds over r squared cosine theta for our dE sub z. But we want to, or we need to put things in terms of, or watch what's changing with, potentially changing with s and z. We want this for a generic z, height above the, above the ring, the plane of the ring. All right, so let's put in what cosine theta is. Where do we have it? Cosine theta is z over r. All right, what else do we need to do? Actually, yeah, well, we're okay. That's okay. We can go ahead and do that now. And so we end up with k lambda z over r cubed ds. And we can go ahead and integrate. R is a constant. Z is actually a constant for what we're considering, so I didn't actually have to do that step there, but we'll go ahead. So E sub z, which is going to be total E, is integral of E, or the integral of dE sub z. So we want the integral of k lambda z over r cubed ds. And like I was saying, these are all constants in terms of ds. Integral ds. And so if we integrate all the way around a circle, what are we going to get when we're integrating the distance, the length all the way around the circle, the ds? We get the circumference of a circle, right? So we're going to get k lambda z over r cubed, 2 pi r, which r, the radius of the circle, which is big R, right? Okay, and so E as a vector then we can say is k lambda z over r cubed, 2 pi r, k hat. All right, just to be a little more complete in terms of the well, depending on how we want to look at it, we can look at it in different ways, but if we want to get rid of the little r and just do it all in terms of the kind of physical geometry here, we can substitute in that r little r is the square root, or we could write it this way, maybe a little bit easier to see. Z squared plus r squared to the 1/2 power. All right, and so we can have k lambda z over z squared plus capital R squared to the 1/2 power cubed, so that'll be 3, to the 3/2 power, 2 pi r k hat is our total E. Thinking about our charge density kind of stuff, if we want to write it back in terms of Q, this is the total length, say the total S, and this is the lambda, so the charge, total charge Q, say if Q is the total charge of the ring, is going to be charge density lambda times the length of the ring, S, which is lambda 2 pi r. So we could write it a little bit differently, pulling those out. We could also say that E is KQZ over Z squared plus R squared to the 3/2 power. Again, don't forget the K hat. Did I lose anything? I think we got it all. And so that could be another way to look at it. This way, if you had the total charge on the whole ring, this way would be more if you have the charge density of the ring and you wanted to figure it out. Different ways we can look at the calculations. Okay. Let's see, how are we doing on time? I have no idea. We'll keep going, I guess. So one other thing we could look at is the charge on a whole solid disk, again through or at a point above the center on the z-axis, for example. Again, hopefully you see the symmetry in the x and y direction, so it would all of E would be straight up. Let's just pick a point somewhere here, and so the whole E would again be just in the z direction because of symmetry. We could use our results and take an infinitesimally little skinny ring like we just calculated, right, and get the dE from this ring, and then we could integrate out over that R, capital R variable we had before to get our total charge on our disk. How would this look? Well, let's set it up a little bit anyway and see how we could do. So we would have a little, let's do this is infinitesimally thin, although it doesn't look like it. Infinitesimally thin ring here, but we're going to have this little width is going to be, let's just call it d little r in this case, and have this be r. Big R be just the constant going out to the full thing, and we're going to have a little r. We're going to have lots of r's possibly here, but let's go with that. And so we've got a little dr distance here, and since we have a flat disk with a surface charge, we're going to have sigma would be our charge density, right, which is charge per unit area. And so if we want our q, say our little dq in there is going to be sigma times our dA, right, and our little piece of area. And our little piece of area, what are we going to use for our integration variable? I guess we'll use dr. Makes sense? All right. And so our dA then is the little area in here. All right. So it's got dr. We think of it as a tiny little rectangle, even though we know it's curved, but in the infinitesimal it look like straight lines, so we can't really see the curve. The curve is huge compared to our little tiny piece we're looking at. And so we're going to take it as dr this way times 2 pi r for the whole, actually for the whole ring. So we'll do the whole ring at a time and then add up all of these rings. So we want the length all the way around here, and so area-wise is so skinny, we'll think of it as straight, but it's really bent. But anyway, it works out in the limit. And so 2 pi r. So thinking of taking this and straightening it out into a big long line, dr wide, dr width, very skinny little line, right? And then the length is the length of the whole circle going around the circle. So that would be, again, a 2 pi r. So our dq in this case is going to be 2 pi r sigma dr. Yes, looks good. All right, we can use our dez from above because we know that our dez this time is going to be our e from before, right, from here, and then we can put in a dq instead and go out, making more and more little rings, right? So we're just going to take our result from before, k, now dq, z squared plus r squared to the 3 halves. We can forget the k hat because we're doing it as magnitude only. And so we get something along these lines for our dez. But now we need to put in dq. It's a little messy. dez, k, z, let's just write this other stuff, z squared plus r squared to the 3 halves, and then we got our dq up there, 2 pi r sigma dr. Just kind of rearranging a little bit there. Hopefully it still is clear what we're doing. Alright, so that's our dez for this whole little ring, right? Infinitesimally skinny little ring. But we want our whole e, which is actually our ez, which is our whole e. And so we want the integral of all our dez's. Alright, so we want the integral, and we got our variable is r this time. R is going to go from 0 at the center to capital R. So we're going to go from 0 to capital R of all these things. Okay, and so I guess we'll just write it here, kind of thinking about what's going to pull out. And yeah, this, we have a little bit of thinking about what's constant and what's not for our ring. So this r that we had from here is the radius of our ring, right? This capital R is radius of the ring. And so in this case now, each little ring has its own radius, so that's going to be changing. So we can't use capital R in the bottom. We're going to have to put a little r in the bottom. All right? So that's going to make the integral a little bit more difficult. But we can pull out 2 pi kz sigma, it looks like. 2 pi k, 2 pi k, z, and sigma, I believe, are all constants in terms of this integration going out this way. And then we can write our integral from 0 to capital R. And what's still inside? We have an r on the top, and we have a z squared plus r squared to the 3 halves power. Of course, our dr is still left. And just because of the way we're going to integrate, let's keep the 2 inside. Alrighty. Looks good. Going back to some fun calculus, and actually we won't go through all the details here, but we can do a change of variables kind of method. We can just call it, I don't know, capital X is what the notes have. We're going to call capital X z squared plus r squared. And then what is dx? Our variable is r, so taking the derivative with respect to r, we'll just get 2r dr. And so when we substitute in, so we've got 2r dr, and we've got x to the 3/2 power, so our integral becomes dx over x to the 3/2 power, right? And so we can go ahead and evaluate that integral, and we get, this is x to the negative 3/2. Okay. So we got the integral of x to the negative 3/2 dx becomes, when we integrate, we add 1 to the exponent and divide by the new exponent, right? And so we're going to have x negative 3/2 plus 1 whole would be just x to the negative 1/2, and then dividing by, that's a 1/2, negative 1/2, negative 1/2, divide by negative 1/2, evaluate between the limits. But let's go ahead and put what x is back in. So we'll have dividing by negative 1/2 is multiplying by negative 2, and then x is this, z squared plus r squared to the negative 1/2 power, or 1 over the square root, kind of thing. And then I don't want to lose all this stuff, so we also have, don't forget all of our constants on the outside of our integral as we're doing our integral. Get those down there. Okay. And I think I'll let you, just for time wise, let you go ahead and put in the details. Hopefully you can get it all to come out to be, oh shoot, we also, in the notes they also use k is 1 over 4 pi epsilon naught to get the format that we have. And we should end up with Ez is equal to sigma over 2 epsilon naught times 1 minus z over z squared plus r squared. Oh, square root. That 1/2 power thing here. Something like that after we put in the limits. All right, so we would see something along the lines of, like you would expect, near the center, if we're looking at a graph versus z, has a peak near the center of this coefficient here, and then it dies off as it goes for any certain z level, but or as z gets higher and higher, that's how it dies off. Okay. But let's keep moving because I think we're running out of time here. Let's look at one more charge distribution. Let's say we have a wire, just a straight line wire, or straight line of charge. Okay, and so it starts here, but it goes on the x-axis to infinity. Okay, in the x direction. Alrighty, and we're going to look at again the field up here at a point above the line. Let's see, what are we going to call things? We're going to call this R, capital R this time, and of course we're going to have some little point that we're going to use as our dq to get our dq for doing our calculations. And so the straight line, so this will be our little r now. We got this point, and so again our field, we'll kind of assume everything's positive, but we know if things are negative we turn the sign around. So then our DE is going to be this way. All right, we're just kind of 2D now. X and, we're going to call it X and Z, X and Y. We'll do X and Y. All right, so this will be our Y direction now. Okay, so do we need anything more here? We'll probably need some angles. We'll call this one theta. We'll call this one phi, just to give things names. And we're going to say this is starting at x equals 0. Just orienting our coordinate axes at the start of the line of charge. Okay, so again we're back to being a line of charge like I just said. So dq is going to be lambda, and then it's the line is just moving straight in the x direction, so it's going to be lambda dx. Again, lambda is the charge density. Our dE back to the KQ over R squared kind of thing. So we're going to have K dq over R squared. And just doing magnitudes would take care of direction with the picture. And this time little r is the distance, so we can use that. And so dE, let's keep going. So dE in terms, or to get it in terms of x and y kinds of things, we're going to need to fix r, because r is going to be changing in size now, little r. Right, it starts out as big R, but then it gets longer and longer and longer as x changes. So little r is not a constant now. So we've got K dq, and little r, hopefully it's fairly obvious, it's the, we'll just write it up here, square root of x squared plus r squared. Right, just Pythagorean theorem, triangle here, x, r, little r. So if we want little r squared on the bottom, we're just going to have x squared plus r squared and the capital R squared in the bottom. All right, that's good. But now we've got to do EX and EY, or DEX and DEY. So let's just write these over here just to keep track of them. So DEX, I'm so good at writing things where I want to write later, but let's make this be the label for DE. So we've got, go straight. The little triangle up here, this will be DEY, and this one will be DEX. Added together, they make DE. Hopefully you can see that. That's not off the page. All right. And so DEX is in terms of what angle? Well, we got phi right here, so we got phi. And so DEX, in terms of phi and E, DEX is the opposite angle, right? So it's going to be DE sine phi. And similarly, DEY is going to be DE. Y is the adjacent angle, so it's going to be cosine, or the adjacent side, so it's going to be cosine phi. Alrighty. So we got DE here, we got that. I think we are pretty good to write our integrals. So let's look for EX first of all. Alright, it's going to be the integral of DEX. We need to, yeah, that's good. Okay, so we can write our integral. Let's just write it and then we'll pull things out in a minute. So our DEX is going to be DE sine phi. So DE, put that in, K D, let's save a space for DQ, and then x squared plus r squared. But DQ is lambda dx. Right, and then for the EX part, we need a sine phi. Okay, I think we're pretty good. Check the notes in a minute. Okay, what did I do differently here? Well, we just have a little bit more work to do. Because phi is related to x, yes. Okay. Okay, well, we were getting there, but we still have a little bit more work to do. So sine phi is not independent of x, so we can't evaluate our integral yet, right? So what is sine phi in terms of x and r and all that goodness? I'm going to draw the triangle bigger down in here so we can see what we're doing. All right, so we've got DE, DEY, DEX, but we've also got Actually, let's look at it in terms of the position kind of variables. So again, we've got phi, and actually this will again be theta, and we've got, actually we can just look at it in this triangle, sorry. And so let's just look at the big triangle to get our relationship between sine and cosine and the lengths kind of stuff. Alrighty. Alright, so sine of phi. Sine of phi is going to be, for phi anyway, is going to be opposite over hypotenuse. Alright, so sine of phi, let's just do a little sidebar here. Sine of phi is opposite over hypotenuse. So opposite in this case is x, and hypotenuse is square root of x squared plus r squared. It is not looking pretty, but that's what it is. Okay, so sine phi is that. If we want cosine phi pretty soon when we do the y part, let's just go ahead and write that here while we're at it. So cosine phi is here, and so cosine is adjacent over hypotenuse, so that's just going to be capital R then over square root of x squared plus capital R squared. Alright, so as dx changes, capital R doesn't change, x does change, little r does change. Alrighty. But we've written little r in terms of x, and so we've got all of our variables written in terms of x being the only variable now, once we plug that in, and then the rest are constants. Looking good. Okay, so ex is, what can we pull out? Not much. We can pull out k and lambda. And then in our integral, we're going to have sine phi for this one. It's going to be x on the top. And then we've got a square root of x squared plus r squared, and this is an x squared plus r squared to the 1, and this is x squared plus r squared to the 1/2. So the total number of x squareds plus r squareds is going to be 3/2 in the bottom, I believe. And then, so that takes care of sine phi. We've got k and x, we've got this one, and so all we got left is dx. Okay, I think we got it. Let me just double check my notes. Looks good. All right, except for I did forget the limits of integration. Not too hard though. We said x is starting at 0 and we're going to infinity, and that, I don't know what that means. Anyway, it's irrelevant at this point. All right, so we've got ex, and we've got a lovely integral to do that has x's, and well, we can do a similar thing that we did last time, right? If we choose our variable of integration, whatever, we can say u is the inside here, x squared plus r squared, and du then is going to be 2x dx. We're going to get a factor of a half. Although I don't know where that went. And then it's going to probably cancel out with the 2 from when we do the integration. So do I need to do it with you, or can we let's just go ahead and, for the sake of time, hopefully you see. So if we say do the same kind of variable substitution, u equals x squared plus r squared, then du is going to be, this time x is a variable, going to be 2x, right? And so we can substitute in, we're going to have 1/2, let's just, so k lambda integral, we'll fix the limits later, and then we'll have, so x dx is du over 2, so this is going to be du over 2, and then this is going to be u to the 3/2 power, and so getting the integral of k lambda over 2, integral of u to the negative 3/2 is going to be u to the negative 1/2 over negative 1/2, and so the 2 and the 1/2 are going to cancel out, and you get a negative sign u to the half. Okay, and so we end up with e sub x, then ends up being, if we plug everything in and plug in our limits 0 to infinity, take the limit as x goes to infinity, end up with negative k over r. nice and neat. Okay, but I'll anyway. So this. Yeah, let's go with that for now because I'm not sure, we might be running out of time. All right, so that's the x component. Is there a y component? So that's the x component. Looking at it, why is there an x component if it goes all the way to infinity? If it was a line that went from negative infinity to positive infinity, we could say by symmetry there is no x component because we have a same amount going this way as going that way. But since it's only half a line, it's all going that way, we get an x component in the negative direction, which that's what it shows us. All right, let's look at the y direction part just for a bit, maybe with some more hand waving though, so we'll see. So DEY, I wish I saw what time we started here, but what's DEY going to be? It's going to be like we have DE cosine phi. DE is K dq over x squared plus r squared, and cosine phi from our triangle is r, big R, over square root of x squared plus r squared. And so overall our DEY becomes what? K r dq over this fun friend of ours, x squared plus capital R squared. We got to the 1 power plus times to the 1/2 power, so add exponents to the 3/2 power. That doesn't say 3/2. 3/2 power. All right, so then our integral, we need our dq in there also, and dq was lambda dx, and so k r lambda dx over x squared plus r squared to the 3/2. And we thought the previous one was fun, but now this one has no x in here, so we have different kind of integration to do. Let's get our integral written here first. And so let's pull out our constants, kr and lambda. So our EY is going to be kr lambda, integral from 0 to infinity of dx over x squared plus capital R squared to the 3/2. Double check. Looks good. Looks good, except for the integral is not a fun one. If you remember back to all of those different kinds of variable substitutions, if you really, I'm not going to do all the details here, but we can use a secant. Yes. So we're going to choose our variable of integration, dx. We're going to say dx is r secant squared d phi, or d I put it together differently than my notes had it, so we can use a lookup table or what have you to get this. I'm not going to worry about the details, and I'm not going to require you to do this on a test for sure, and probably not in the homework either. But going back to your calculus, either a lookup table, or I think it's a substitution for x is related to secant or secant squared or tangent. Let me see. If dx is secant squared, that means x must be tangent of a new variable theta, and then a different variable, and then we substitute in. But going through all the details, evaluating the integral 0 to infinity. So again, we get some limits, or no, depending on if you change the variable, what its limits are. Being careful with all those, we again end up with k lambda over r. Okay? So magnitude-wise, it's the same. Remember, Ex was negative k lambda over r. And so they're same size in magnitude, which is kind of strange, but different signs. So the total E then is, I guess, k lambda over r, and then its direction is negative I hat plus j hat. All right, just factoring out the pieces, putting it all together. So this is the field. Remember, what in the world were we doing? It's the field from a straight line of charge that goes infinitely out in one direction. We'll have a electric field that is basically at a 45-degree angle going out like this, which kind of makes sense looking at the picture and thinking about the symmetry of it. Okay, so like I said, I didn't do a timer, so I don't have any idea how long that took, but thanks for sticking with me, and we will we'll move on next time to looking at some other things. If you have questions and stuff for the homework and stuff today, be sure to send me an email, and I'm not sure, depending on the weather, I might come in this afternoon or might not. It's still looking like the icicles are getting longer, but we'll play it by ear. But keep track of homework and achieve. Keep me up to date on what you need, and I think we'll call it quits there.